afternoon. I'm Chris Paxson. I am very glad to welcome you to Brown's Family Weekend Keynote Address featuring Peter Norvig, class of 1978 and P16. He currently serves as Director of Research for Google. We're fortunate to have Peter's daughter, Bella, as a member of the class of 2016. And we're delighted that Peter accepted our invitation to speak to the Brown community this weekend. Peter began his relationship with Brown as an undergraduate, concentrating in applied mathematics. After receiving his bachelor's degree in 1978, he transitioned into the world of computer science, earning a Ph.D. at the University of California, Berkeley. He spent time as an assistant professor at USC and at UC Berkeley, but he spent the majority of his professional career in industry working on software engineering, artificial intelligence, and natural language processing. Peter's career has been marked by persistent intellectual curiosity, a distinctive Brown characteristic, and a desire to test conventional wisdom and theories. His work in software development for what is now the Intelligent Systems Division at NASA's Ames Research Center allowed robotic spacecraft to operate autonomously, and it set the stage for the success of the Mars rover. For his contributions, he received the NASA Exceptional Achievement Award in 2001. From 2002 to 2005, he served as Director of Search Quality at Google. He then moved into his current position, leading the machine translation team, whose projects include language translation, improvements to image search capabilities, and speech understanding for voice-activated applications. This work revolves around the idea that challenges can be solved by aggregating huge amounts of data and analyzing the patterns that they produce. As a recognized leader in the field of artificial intelligence, Peter has co-written an essential textbook on the subject and authored more than 50 publications. He also co-taught a massive open online course on the topic for Stanford, which had 23,000 students who completed the course. He's a fellow and counselor for the American Association for Artificial Intelligence and the Association for Computing Machinery, and has been elected as a member of the American Academy of Arts and Sciences. At Brown, he serves as a member of the External Advisory Board for the Brown Institute for Brain Science, which supports a very active group of faculty, students, and researchers focusing on artificial intelligence and building brain-like machines. He's also spoken to undergraduate and graduate students here in the Computer Science Department about the effectiveness of data. Peter's enthusiasm for his work is obvious. His vision in helping us to improve the way we retrieve, use, and understand the overwhelming amount of information available to us. We're proud of the contributions he's making to both industry and to education, and we value his continued engagement with the Brown community. So please join me in welcoming to the podium Peter Norvig. Thank you.
Thank you, President Paxson. That was a great summary of the work. I feel like maybe I don't need to talk anymore because you covered it all. But what I do want to talk about is what can we do with all this data that's available now? So much more of our lives are in form that's captured as computer data. And how does that affect our lives? How do the computers work with that? How can they make sense of it? And how does that change what we do and, in fact, change all of society? Now, the history of the 20th century started off dominated by American workers like this, tough laborers. But in the second half of the 20th century, we started to transition more to laborers like this. So here's IBM's Thomas Watson, class of 37, and a couple of anonymous programmers. And more of the work began to be more this knowledge type work rather than physical work. Now, what were they producing? Well, they weren't building ships and tanks and cars and things. Rather, they were producing lines of code like this. Very long, detailed, precise, step-by-step instructions of exactly what you wanted the computer to do. And those of you who are computer science majors know that sometimes it can be frustrating and you get it wrong. And you also know that this type of learning, of instructing the computer step by step, is quite different from the type of learning that we do. So here's a picture of me learning from my mom several years ago, although this actually was in Providence. So you forgot, President Paxson forgot to mention my first connection was that my dad got his Ph.D. here. And so I was in Providence at the time. And notice how do children learn? Well, they don't learn by being instructed step by step the way a computer is instructed. They learn by observing the world, by doing, by touching and interacting with the world, and sometimes by listening to teachers and mentors. And I should say my mom went on to be an English professor, but at this point I was her main student. And here, just for symmetry and balance, is my dad, and he was a math professor. And I guess I should say, you know, if Google is a successful combination of words plus math, then maybe I'm the combination of mom and dad. And all you students are here should turn and thank your mom and dad for contributing whatever they did to get you here. So I arrived in 1974, and I learned how to program computers here, but I also learned other stuff. Here I am at Pembroke Field. I'm studying the aerodynamics of rotating disks. That was a big part of my studies. But notice that there's no textbooks involved, and there's no equations, no classrooms. This is learning by doing, so a very different type of learning. And so there's this shift from learning by explicit instructions to learning by observing and doing. And that's what we as people are really good at. And if we ever want to get our computers to do more, to not have to go through this laborious practice of programming them, then we're going to need to have this. Okay, so I'm going to show you some examples of how we can do that. How can we teach our computers the way a child learns, by example. And the first example is in robotics, and this is a new robot called Baxter. It's just been out for about a year or so. And most robots you program laboriously with those instructions. We've gone beyond the green and white fold paper. You now program it on a screen, but it's step by step. Baxter is different. So with Baxter, what you do is you grab his arms and you say, here, take this arm, move it over here, pick this thing up, and now move it over there, and you just show it how to do stuff. And then it learns to generalize. So you go through the steps, you say, go over here, do this, and then Baxter can now, on his own, pick up stuff coming down the assembly line, and maybe they're in not quite the right position, a different position each time, but it figures that out, figures out how to pick them up and put them in the box. And although you showed it how to put one in one corner of the box, it knows that the next one should not go in the same place, it should go in a different place. And so it's kind of a partnership of you demonstrate, and it figures out what to do next. Right? So a much more natural way of instructing the computer. And notice what this says for our economy, right? That we're worried about jobs disappearing by animation, and if the only jobs that can be replaced are jobs that require a bachelor's degree in computer science, then we're in trouble, because not everyone's going to be able to get that degree. But if they can be replaced by a factory worker who you can say, now instead of doing the physical labor, your job is going to be to instruct robots, then most anyone can do that. So that's a good sign. There's lots of other places where this type of thing can work. Let's switch to a very different one. Suppose you were a historian. You don't normally think of a historian as being a computer programmer. And let's say you had this question of, you know, there's two views of what the United States is. So the United States, that's plural, it's a federation. But we also think of us as a single republic, one nation, indivisible, and so on. How do those two views relate to each other? And historically, how has that changed? How have we switched from one view to another? Well, if you're a historian, probably the way you think of approaching that is saying, well, I got to go out and read a bunch of books. And I'll read some primary sources, I'll read some secondary sources. If I want to track that over time, I'm probably going to have to read hundreds of books published in different time periods. And it's going to take me a really long time to do that. Now, is there a shortcut? Is there a way to summarize everything that's in those books relating to this question without having to read the whole books? And the answer is yes, there is. And in fact, Google has done such a summarization in that we have a list of all the phrases that are in all the books by publication year, and we allow you to query that. And so a clever historian could figure out just the right phrases to ask to answer that question. And here's what one did. They came up with the two phrases, the United States is in blue versus the United States are in red, singular versus plural. And then you can see the plot over time, and you can see that there's a crossover, if I can get this right, right about here, which it looks like it's 1879. Right? So before the Civil War, we thought of the states as being independent, and about 10 years after the Civil War, we started to think of ourselves more as a single republic. And you can do that in a 10-second search rather than in years of reading the source literature. Not the definitive answer, but a great new tool for doing things like history. Okay, here's a more technical example. Problem of word sense disambiguation. What does that mean? Well, you have a word like bank, and it has multiple senses. The two main ones are this river bank and money bank. And now, if you're given a sentence that has the word bank in it, how do you know which one it means? And this is an important task for things like search engines, because if you do a query with the word bank in it, we want to show you results that have the right one. So we want to understand which bank were you talking about. Now, how can we do that? Well, I'm going to promise you that throughout this talk, we're not going to have any math equations. So we're going to solve it by analogies rather than by equations. And you can pretend that the equations are there. So here's an approach to solving it. So we have our definitions written in our dictionary. And we take out our scissors, and we cut up the definition. And we take each individual word and throw it into a paper bag. And we do that for both definitions. So now we have two bags of words. And there is a technical term for this model. It's called the bag of words model. I'm not making that up. And in the first bag, there's all those words that came from the definition. In the second bag, there's those words that came from the definition. Now, one of my heroes is a statistician, George Box, who says, essentially, all models, all statistical or mathematical models, are wrong, but some are useful. And once you admit that, then you say, well, maybe I shouldn't worry so much about getting the right model. And maybe I should just steam ahead with the wrong model. So the bag of words model is one of the world's most wrong models, but it's very useful. So what the bag of words model says is, I want to model what language is like. How could a sentence or a book be produced? And it says, my model of how it's produced is you take all the words, you put them in the bag, you shake it up, and then you draw the words out one at a time, and you paste them next to each other. Now, obviously, that's really, really wrong, because words aren't independent of each other, and where one word is, and the following word, and their sentence structure, and so on, those are all important. But even though it's wrong, it turns out it can perform pretty well. And if you have the right amount of data, it's more important to deal with that data in a principled way than to have the absolutely right model. So what can you do with this wrong model? So here we are, we have these two bags of words, and now we get a sentence, and we want to figure out which sense of the word bank does this sentence belong to? Where did it come from? And our model says, well, either this sentence was formed by randomly pulling words out of bag one, or it was formed by pulling words out of bag two. It's got to be one or the other. And which one is more probable? And here we'd say, well, it's more probable it came out of bag two, because we know the word loans is already in that bag. And that's basically all there is to it. And now the crucial step is, after we've done that, now we can make our models better. So our model started out by saying, all we know about bank one and bank two is what comes from the dictionary definition. Now we know a little bit more. And we can take all the words that are in this sentence and throw them into bag two. So bag two gets a little bit better. It covers a little bit more experience of the world. And now we go on to the next sentence and try to do the classification of that. And eventually we get to the point where there's lots and lots of words in each bag. We learn new vocabulary words, and we count which words appear lots of times, and so some of them are much more frequent than others as we get more and more examples, and the two bag models get more and more precise. And that's basically all there is to it. That's the amazing thing. And so essentially, you could say that everything I needed to know about language processing, I learned from Sesame Street. 1, 2, 3, So we do these counts, and we go back to sentences, and now we know more and more of the words because we've seen more of them, and we can get more and more of them right. How well can we do? Well, this is from a survey paper that looked at 4 different algorithms for performing this task, right? So they all have something like this bag of words model, but the details of how you measure how close a sentence is to the words in the bag, those details can vary a little bit, and there's 4 different algorithms or techniques for doing that, and they have those funny names. The names aren't important, and here's the scores, right? And so if you have 1 million words of training data, 1 million words worth of sentences that you throw through here, and so the total number of words in the 2 bags is 1 million plus however many words there were in the original definitions, then these are the results. It looks like the blue one is the best, and its score is 85% correct. So that's pretty good, right? 50% would be random. You can get 85%. But now, if you go out and get 10 million words of training data, now you're doing a lot better. And all of a sudden, this blue model, which everybody thought was the best at 1 million, is now the worst, and we're up to 92%. And you could stop there, or you could just go out and get 100 million words, and it gets a little better, or 1 billion words, and it gets better still. And these charts like this changed the way people thought about how we were solving this problem. Because in the old days, all the academics were arguing at one point, like they were arguing here, and say, blue is best. I got a better score, so I get to publish a paper. And then somebody else would say, no, I like green, I like red. They were all arguing over the algorithm. And then we realized that when you argue over the algorithm, you get small differences here. But if instead of doing that, and that's a lot of work, if instead we just go out and gather more data, then you get a big difference. We moved up, with 1 million, we were 82 to 85%, but with 1 billion words, we're up at 97%. And it's a lot easier to just go gather more words, just copy them off of the internet, than it is to come up with a new clever idea. And so people have changed the way they think about what's important and focused it more on gathering the data and having an algorithm that can work with it. In a sense, you could say that Google is really founded upon the idea of looking for these types of problems. These problems where schematically, when you have a small amount of data, it performs poorly, and when you have a large amount of data, it performs well. So we try to find places that have a curve that look like this. Not all problems can be solved with more data, but we find the ones that it does work. Okay, next task is going to be a little bit tougher. It's the task of machine translating from one language to another, English to Spanish or whatever. And there are examples of this out in the world. So you can go out and gather examples of text. So here we have 2 texts, one in red, one in white, and a version in English and Spanish. And we could drive around the world looking at signs, but it's probably easier to surf around the World Wide Web and find documents and find a correlation. Here's a document in English, here's one in Spanish, and that's easier because we can find millions and millions of those. So now we have all these, what can we do with them? So we've got this correspondence. We said, here's a document in English, here's one in Spanish, and we know one corresponds to another because we were sort of told that on the sign. Now, if somebody asked me for exactly this sentence in English, I can say, ooh, I know the answer, and spit out the Spanish. But they're probably not going to ask me that. They're probably going to ask me something I've never seen before. And in order to do that, I have to understand better not just this one-to-one correspondence of sentences, but I have to break them up into pieces. And so what I want to be able to do is say, here are the phrases, and here's how they correspond to each other. And some of the phrases are out of order. So I want to be able to go from this original input, break it up like this. And because I promised I won't use any equations, I can't tell you exactly how to do that. But the intuition is, if you only saw this one example, you'd have no way of doing it. You don't know what the word security refers to. It could be any of the words in the bottom there. But if you see lots and lots of examples, you start to see patterns. And hey, a lot of times when the word door is mentioned in English, this word puerta is mentioned in Spanish. And so maybe they correspond to each other. And then it's like doing a jigsaw puzzle. Once the first piece is in place, the second piece becomes easier, and pretty soon you have this complete correspondence. Now, I talked about the bag of words models. This model has been called the refrigerator magnet model, because it really is like having these little phrases on refrigerator magnets and sliding them around on the door. And how could that possibly work? To translate language, don't you need to really understand what's going on? Isn't it more than just moving refrigerator magnets around? Well, to get 100% right, yes, you do need to understand more. But to get 95% right, turns out this is all you need. So what exactly is a refrigerator magnet model? It has 3 parts. It's a little complicated. The count's coming back again. So we have to count up how many times we've seen each phrase and how many times security alarm is joined with something else in Spanish with this particular phrase, and maybe security alarm also has another possible translations into Spanish. Then we also have a target language model. So the translation is bilingual, the target is a monolingual model, and that's saying out of all the translations that you could have picked, maybe there's 2 equally good translations in terms of how often they align with each other, but you want to pick one that sounds really fluent. And so the translation model is how often do you see particular phrases in the language that you're trying to translate into, so you can pick those good fluent phrases rather than the weird ones. And then there's this movement model that says when you saw a phrase, was it shifted to the right or left on your refrigerator? And we have to remember that. Now, from Spanish to English, there isn't that much movement because they're both subject, verb, object languages, but in other languages, there's lots and lots of movement, and you need a model of that as well. So this is a wrong but useful model for translation. We're going to show how it works. So imagine we built up this database. We went out, we found millions of pages of English and Spanish. We broke them up into pieces. We built that database with the 3 models. Now we're given a brand new sentence we've never seen before. It's not in the database, or we want to be able to translate it. So how do we do that? The first step is we choose a way to break it up into pieces based on what are pieces that you've seen frequently before. Then the second step is you choose translation for each piece. Again, just based on the counts. What's the most frequent translation for each of those pieces? You've seen them before. Then the third step is you choose to move pieces to the right or the left based on which pieces have commonly moved before. In this case, I've chosen not to move anything to keep them in the same spot. And the next step is you consider other possibilities. So you don't choose just the most probable, the most common, the one with the highest count. Rather, you choose multiple possibilities and examine each of them. And then you evaluate each one to find which one has the highest total probability, and you say, okay, that's going to be my final answer. And that's all there is to it. Right? So it's just the count in the end. But you have to be clever about how you, what you're counting and how you break things up. Okay, one more example. Moving away from words, and this time we're going to look at images, at pictures. And here's a screen from the Google self-driving car. It takes pictures of the world as well as other sensors that it has, and it's important for it to recognize objects. So it's really a good idea for it to know where the cars and pedestrians and bicyclists are so it can avoid them. And I'm going to tell you how you go from an image to picking out these objects in the image. And I'm going to do that by way of an analogy. So here's the analogy. Suppose you had a business selling ceramic tiles, and you had nicely decorated ones, and you have a catalog of tableaus like this one that customers can choose from, and they say, yeah, for my kitchen backsplash, that's the one I want. But then you want to expand, and you say, wouldn't it be a great idea if the customers could upload their own picture, and then we would make a set of tiles, put them in a box, and ship them out. Maybe we get more customers that way. But the finance guy says, no, this is terrible. It doesn't work because it's very expensive to create just one tile of a particular color and shape. What we really need is to have large runs of thousands of tiles, and then we can get our costs down. So you say, well, how can we do that but still have customization? And you come up with the idea of saying, well, what if we had an inventory of common-looking tiles, and then when somebody uploaded their picture, we'd go into inventory and find the combination of tiles that were closest to their picture. It wouldn't be an exact match. It would be off by a little bit. But, this is not, we're not going for photorealism, so that's okay. Now you could have a limited inventory, a set number of different tiles, and you could still represent, close enough, lots of customers' pictures. Now the question is, what goes in the inventory? What are the important pictures that kind of represent the world? And if we have that, then we've learned something really valuable. We've said these are the pieces that are common in the world. We've broken up the world into important pieces. We've understood something about the world. So how would you figure out what the best pieces are to put in inventory? Well, you'd look at what the customers are sending you. So you'd say, here's all the pictures that customers are sending us. What are the common pieces that show up again and again there? And people tried to do this, not for tiles, but for computer vision, to try to say, what is it that images are made out of by having a restricted inventory. We don't call them tiles, we call them basis functions, but it's the same thing. So we said, if we're restricted to having a set number of pieces, what should those pieces be? And in 1996, work at Berkeley addressed this, and they worked with black and white rather than color, and they said, I'm going to have a set number of pieces. What are the best pieces to most closely represent all the pictures I've seen? And the answer was this. And if you look at it, it says, well, the answer is lots of lines. Lots of lines in different positions and different orientations. And that makes a lot of sense, because anybody with a pencil or charcoal knows that you can draw a lot of different stuff with lines. So in one sense, it's the right answer, but it's not a very interesting answer. And then work went slowly for another decade or so. And then the field came up with this approach of saying, well, maybe we can go through multiple steps. So the problem was, as we went from our pictures into this inventory, all we got out were lines. But what if we don't stop there? What if instead we say, now we're going to take all these lines and we're going to put them as input into the next stage and have an inventory at the second level. And at that second level, we expect, rather than the pixels combining together into lines, now the lines will combine together into something else. We can do that again at the third level, and maybe we'll get something out there that looks like really coherent objects in the world. So it seems promising. Tried it in 2009 or so. It started to really work well, in that we went through this three-step process. At the first step, with similar types of lines, but look what we got at the second and third step. So if you put faces in, at the second step, you actually get out eyes and nose and mouths. It's recognized that these are objects in the world. Nobody told the computer, hey, look for eyes, look for noses. It figured it out on its own. And at the third level, you get the faces back. Similarly, if you put in cars, you get out doors and wheels. And at the third level, you get the cars back. And if you have a combination of lots of different things, it very efficiently allocates its available inventory to all the different classes of things. So that's pretty interesting. That was work done at Stanford, and then we picked it up and said, well, what Google can contribute is a large data center, and we can run models that are about 100 times bigger than anybody had ever tried before. So both in terms of the number of pictures we can look at, the size of the pictures in number of pixels, 100 times the computing power, 16,000 computers involved, and basically an inventory of 1 billion parts. And we did that, and we said, let's train up this system, and we're going to give it 10 million frames, still frames, from videos from YouTube. And we put those all in and said, now let's see what objects are going to come out at that third level when we put YouTube in. And perhaps not surprisingly, when YouTube goes in, the answer out is cats and people. And other stuff too. So these were just two of the available inventory, the pieces that came out at the third level. And this was the best representation. You got to squint a little bit to, you can see it, it looks like a cat, it's okay? Yeah. So that came out. It recognizes that there are such things as cats in the world, and there are such things as faces. And then we asked it, for this object that you recognize, what are the photos that look most like that? And it came up with this. So it can recognize all those cats and all those people. But of course, those are just two of the many pieces in inventory. Here's some of the other ones. So some of them are abstract things, textures like little dots. Some of them are diagonal lines going up and going down, circles. And then some of them are more concrete. So yellow flowers, zebras, wine bottles, and pizzas. So the system has actually recognized that there is a class of object in the world which is pizza. It didn't come up with the name pizza because we didn't give it any words, we only gave it pictures, but it says these all go together, these are pizzas. So it's learning basically what college students learn. Right? Okay, and this is very exciting, and we've applied this to other things as well. In some cases, doubling the accuracy of what we've been able to do. We applied this to speech recognition. And speech recognition is a pretty mature field where it's gotten better and better over the years. And the workers in the field said, yeah, you know, we expect any new thing to add 1, 2, 3, 4% improvement in accuracy. And when we put this new multi-level, 3-level inventory model in, it improved the speech recognition rate by 30%. And the researchers said, we never thought we'd get another 30%. You know, 10 years ago, we got 30% every now and then. We thought that would never happen again. But it happened this time. So maybe there's something that's really close to how learning really works in saying we can aggregate at these multiple levels. And by saying we're limited, we're going to give ourselves a budget of the number of concepts we're able to represent. The concepts that we come up with seem to be important ones. Okay, so that's what we've done. Let's talk a little bit about the future. And I always get inspiration of the future from science fiction, and one of my favorite authors is Douglas Adams. And in The Hitchhiker's Guide to the Galaxy, our heroes, the intergalactic hitchhikers, find themselves aboard this gigantic spaceship in which there are thousands and thousands of people in suspended animation. And they meet the captain of the ship, and they say, well, what's going on? And the captain explains. The captain says, well, you know, we were told that our planet was doomed, and everybody had to evacuate. And they decided that there should be 3 arcs. And on Arc A were all the scientists and artists and creative thinkers. And on Arc C were the engineers and builders and people who actually built stuff. And then in Arc B were the bank tellers and insurance salesmen and telephone operators and so on. And for some reason, they told us that everybody should load up on Arc B first and blast off and leave. And they promised that Arc A and Arc C would be leaving pretty soon now. But we haven't actually heard from them lately. So that's the way that story went. And in our society, back on Earth, we don't blast off anybody into space, but we certainly are blasting away those Arc B jobs. Right? So they're all being replaced by automation. We don't have as many bank tellers now as we used to. We can do a lot of these things online, and so those jobs are going away. Now, the Arc A and Arc C jobs are still around, but some of those are also being threatened. That automation is replacing them to some degree, too. So I think what we're going to see in the future is that the people who are going to be successful are the ones that can use all these tools and work together. So it's not that it's people alone or computers, it's the teamwork of the two of them together. And one of the analogies we see in that is in the area of chess. For many years, of course, people were the only things that could play chess. Then there were computers that were really terrible at it. And then we got to the point where computers were better than any human chess player. But even better than the computers is the teams of humans and computers. And so there's a style of tournament called freestyle chess in which you can have a team of people and you can have any number of computers you want, and the people consult the computers, set them to doing various tasks, and then the person makes the final call on what move to make. And no computer can beat that computer-human team. And I think we're going to see a lot of that. I talked about how that could happen in history, in economics. A lot of authors are talking about, you know, things got too complicated. Now I think what we're going to see is people analyzing data and coming up with models that relate that data, and not so much just coming up with theories on their own. So we'll see more of this type of integration. There's a great example, a new movie out now is the typical cop buddy movie where there's 2 cops are assigned to be partners, and what I saw from the trailer, at first they don't like each other, and I bet it's going to end up that they're going to end up being good friends. That's just a wild guess on my part. But the twist to this movie is that one of the 2 cops is a robot. And I think that's very timely, right? So that's what we're going to see. So not necessarily that you're going to have a humanoid robot, but that you're going to be working more with automated tools, that you're going to be working more with data. It's not so much what can I produce on my own, it's what can I analyze, what can I draw on everybody else. And I think that's great, and I think it's going to make a lot of the work be more social. So in science, rather than saying my job is to go into the lab, produce results, and then write about those results, instead my job could be to gather and integrate and understand results that other people have come up with. And there'll be more teamwork, both person to person and person to machine. So that's what I see for the future, and we can open it up for questions. The easiest is to go to these mics in the aisles, or if you have a really loud voice, you can just yell out.
So this is fantastic. Sounds great. It seems to work right until it doesn't. So what happens and what things are in place to prevent cataclysmic shifts in thinking? So for instance, let's say tomorrow morning we all wake up and we find out that vampires are real. And there's been 5,000 years of fiction that says, well, vampires exist in literature, but they aren't real. But all of a sudden we now have concluding evidence that they are real. How long would it take, or what things are in place for this model to catch changing information like that? And how does that get incorporated?
Yeah, so I'm not sure about the vampire question, but I know this is a really important question that we face all the time. And I think probably the biggest change from the academic subject of machine learning to what's done in practice at a place like Google deals exactly with this question of time. Because all the academic models say, well, the way it works is you gather a data set, and that's sort of sacrosanct, and that's one object, and now you analyze the data set. But we don't have any data that's like that. Instead, what we have are data streams that are coming in and always being updated. And so we have to adapt all the existing algorithms to say, well, we got to be able to work continuously. And now there's always a trade-off, that if today is different than yesterday, does that mean that we should throw away everything that we learned before? Should we drop off just a little bit? What changes should we make? And that's a tough question. And some of that could be where we really need this partnership of humans and machines, where the machine could sound an alert to say something's really different today than it was yesterday. I don't understand what's going on. And maybe the human could come in to help out and say, oh, well, it's different just because one of your inputs machines crashed and you're not getting what you used to get, or it's different because zombies attacked. Let's go this side.
Yes, do you pay attention to the work of Ray Kurzweil, and do you think that computers will have souls?
You know, I'm just an engineer, not a philosopher. So I think that computers and people are very different things. I think we have to learn to work together. And I think that people will start to be less concerned about that question, and they'll just accept the partnership the way it is. And I think we have some experience with that. So I love my dog, and I think my dog loves me, but I know he's not a person. He's different in some way, but I still have an experience with him. And people are used to that. I think we'll gain more and more of these experiences with robots and so on, and we have a tendency to personify them, and we'll have relationships with them. But that's been going back a long time, right? So, in the dawn of computer science and artificial intelligence, Alan Turing, one of the founders of the field, wrote this prescient essay on what artificial intelligence will be like, and he listed some tasks that would be difficult to do. Write a sonnet was one, and then fall in love or have somebody fall in love with you. And I think he missed something there, because even in his day we had that technology, right? So the teddy bear was a technology that made people fall in love with it. And not because it was so good at simulating love, but just because people like to project that feeling onto them. And I think that's the way our society is going to go, that we're going to learn to do these projections onto our machines, and we're going to accept them into our lives in certain ways, and we'll adapt to that. And I think we'll stop worrying about these questions of are they real or so on, and just accept them for what they are. Let's go back to the slide.
I wondered if you've given any thought about when you talk about the future, what the implications of this would be for politics or governments. In other words, I know nothing about it, I just thought it was a fascinating talk. I could imagine that there are some forms of government that would be very vulnerable to this type of thing, because the power of the information all of a sudden would switch radically. So if you think about a more totalitarian type of government type of thing, that all of a sudden people would have much more information than the government would, that type of thing. Yeah,
so there's a lot of issues there. I think part of it is that inevitably this makes things more symmetric, in that the government may have some information, but the people do as well. And it's not just information technology, it's also communication technology. So the fact that the government knows something isn't as important as the fact that they can't really cover things up. They can't shut down all communication. And we saw that in the Arab Spring. It wasn't that there were sophisticated machine learning going on, but there was Twitter and just cell phones and other means of communicating, and that was really important in a weapon and sort of countering these totalitarian governments. And so I think we'll see more of that. On the other hand, there also is this tendency that the rich get richer. And so the people that are best able to exploit a new technology are the ones that are the richest, the most experienced, can hire the best people to work for them. And so I think we'll see more inequality in terms of income inequality and access to information and so on. I think we'll see fluidity in that somebody from the bottom can rise to the top, and you'll see small numbers of that happening, but you'll see more of a divide, that the rich will get much richer, and that's a problem we have to deal with. Yeah.
So piggybacking onto the question of machines having souls, I wanted to ask about where you would say the line is drawn between artificial intelligence having consciousness that compares to a human, and also how, if machines can develop sort of parallel to human consciousness, would there ever be a point where they could reproduce or mimic kind of organic life form reproduction?
Yeah. I guess I think, so we don't really understand what consciousness is, and both what it means for people, what it means for other animals, and how close are they to people, and what it might mean for machines. I think the answer is probably going to be, we were asking the wrong question. That, we're not even on the right track for what consciousness is. And as we start to understand the brain better, we may have better questions and answers for that. So I don't think of computers as having consciousness, but I think of them as actors that can do things. And sometimes it's easier for us to think of them as if they have consciousness. And it's going to be an interesting time finding the answers to all those questions. Yeah.
Hi. Thank you so much for such a fascinating talk. Like you, I'm a parent of a class of 16 person here, and I would love to know from you what you think are probably the one or two most important parts of your college time that sort of made you who you are today? Or, put another way, what were the basis functions of your Brown education?
Yeah. I guess for me, the most lasting things is my classmates, right? That these are people that I kept on running into throughout my professional career. And, and yes, I have had relationships with the professors here, some that are still here, and they were important. But it was really the classmates, and it was, studying late at night and working together with them, and then it was growing up through grad school and professional career with them and keeping in touch. And so I think that's what makes it special.
Hello. So I noticed that in your in the lecture you just gave, that you stayed very far away from the code aspect of getting all these technologies that you described to work. And then you also explained that in the future, we are going to be able to allow people that don't have as much experience with coding to be able to interact with computers as easily as I'm talking to you now. But at the same time, just looking at technologies that presently exist, there's always still this fundamental need to code. So do you think that at some point we're going to be able to use this idea of collecting up all this data to do away with code, or do you think the code's going to be and remain a fundamental part of computer interaction in the future?
Yeah. I guess I think of two classes, right? So it's like with other technologies, right? So with cars, we build cars so that anybody can learn to drive them, but only a small number of people have to know how to design them. And so I think it'll be the same thing with computers, and maybe we're at a point now where we might have too many people that are designing computers and programs, and that's only because we don't have a good way to communicate with them. And so probably over time we'll see more people that are users and are much more facile users, right? So today, if you call yourself a computer user, it means you can log in and remember your password and open up a document and save it and format it and so on. I think in the future we'll expect these type of untrained, non-programmer users to be able to do much more, to do these types of analysis that I'm talking about. And you're right that behind the scenes there'll still have to be the experts whose life is dedicated to making it easy for all these people to do that. And that's not going to go away. Now, the exact way in which they do that will probably change. You know, we'll have different programming languages and different programming environments and so on. But there still will be a separation between the class of builders and designers and the class of users.
Hi there. From what I understand, Google's machine translation tends to be most accurate between related languages like English and Spanish. And I'm wondering, what's Google doing right now to try and improve its algorithm for languages that are unrelated?
Yeah. So a bunch of issues there. So it's most accurate, you're right, for languages that are closely related in two ways. One is if they have a bunch of cognates, so English and Spanish have a lot of roots, or English and German have a lot of roots. Secondly is if their structure is the same, subject, verb, object versus other possible structures. So the more we have that, the better. Also, the more training examples we have, the better. So there's a huge corpus of English to Spanish translations that we can draw on, and that makes that work really well. If we wanted to go from, say, Latvian to Tagalog, there's not a lot of documents that translate directly between those two languages. So what do we do in cases like that? Usually what we end up doing is triangulating. So we'll make a two-step translation, say from Latvian to, I don't know, English or Russian, whatever we think we can do best, and then from there into Tagalog. And you'd think you'd double or square the number of errors in going two steps. Actually, it turns out it's not that bad. I think because what happens is it ends up making two mistakes, but in the same place, so that it's just one mistake overriding the other mistake. So that works pretty well. I think we're doing more in terms of having multiple paths, right? So here I said I could choose one path from one language to another. What if I could try 4 different paths through all the languages I knew and then aggregate them together in one way? So we're starting to be able to do that. We did that in languages like Yiddish, where we had a very small number of total corpus, but we said, well, let's look at the related languages, Hebrew and Polish and so on, and try to blend those in. So that's part of it. And then we're also trying, you know, what I showed was this pure refrigerator magnet model where the only notion of a phrase was words that are next to each other. We're now adding in the traditional syntactic noun phrase and verb phrase, and that makes it easier to move a part of a tree rather than to just move consecutive words, and that helps as well.
Another question about machine translation. So one can imagine a lot of cases where you have entire sentences whose meanings are very, very different depending upon context and would have a very, very different translation depending upon like whole, you know, paragraph context or whole multiple paragraph context. So what sort of work is being done to address those sorts of problems?
Right. So that's a great question, and so far we just haven't addressed it. So we do the translation one sentence at a time. Even if you give us a whole paragraph, we do it one sentence at a time. And the reason we do that is because we want to, like you give us 10 sentences, we'll ship them off to 10 different computers, and so it will come back in 1 second rather than in 10 seconds if we'd done it consecutively. And we did it that way because we said, if we had this context-aware multi-sentence model, we know we could do better. But one, it would be much more expensive to us to keep these models because the models would become larger. And two, it just turns out that right now it doesn't get that much better, so that we find our users would rather have the speed of an answer that's not quite right rather than a little bit more accuracy. But certainly it is the case that the exact same sentence can mean different things depending on the context. The thing we get wrong the most is the pronoun references. So if you have it in English referring to something in the previous sentence and you have to translate into a language where you have to choose, is it going to be masculine or feminine? Well, you just don't have any way of choosing at all if you don't have that context. And so I think the next step for us is to try to put that in. Rather than say we're going to try to translate the whole block at a time, let's just try to pass just that little bit of information from one sentence to the next. I think that will help.
Hi, first, for those of us that are not that technologically savvy, thank you for voice recognition software. There's probably got to be just a plethora of ethical considerations that corporate America and Google must take into consideration with this. I think of the Terminator movies and how we create machines and then they destroy humankind. Where should the responsibility lie with respect to the ethical considerations as we increase our abilities within the technological world? And how is Google looking at that? And how are they handling it?
Yes, it's a tough question. We think about it all the time. I should say we've already built machines that have destroyed part of humankind, right? So we build lots of very powerful war machines and we go out and kill each other more effectively. In a less obvious way, we built lots of automobiles, and though those do very good things for us, they also pollute the cities and change the way the culture works and so on. So they've had a big effect. And nobody's in charge of that, right? It just sort of happens over time. I don't think we want to have central planning to say you're not allowed to have automobiles because bad things might happen to the city. I think that's just an ongoing conversation of how does this technology work, where is it going, is that the right place we want to go. Now, the more technical aspects, yes, I think the companies developing these things have a responsibility. So we work very hard to say, what are the possible failure points and how can we protect against that, mitigate any damage if something goes wrong. I'm not really worried about this Skynet computers taking over because I think we know how to not do that. But there's lots of other security and privacy type things that are an issue. And so we have to be careful, have sort of a level of professional responsibility that says, here's the problems we have to look out for and make sure your software deals with that.
Thank you.
My question actually was very similar on privacy. And my question really is, I know you're saying essentially there are ethical issues and companies need to be there. One might question whether that is enough. But I'm curious about technically how much you can take the big data and tell personal things about each of the individuals here, because I do think that's a concern.
Yeah.
And a related question there is the NSA issue and what your thoughts are generally about the danger of pulling big data to be able to do things like that.
Yeah.
Thank you.
So I guess different companies are interested in doing different things. I think for Google, we're more interested in data that tells us about everyone rather than data that tells us about you. And other companies have different mixes. So I think like Amazon is more interested in you because if you're buying classical music today, you're probably going to do the same thing tomorrow. And remembering that about you is important. Whereas for Google, you come to Google more because you want to learn something that you don't know rather than to repeat something that you've done every time. And so we're more interested in saying, how is this class of people that did this thing once, how can we form that large class rather than what do we know about you in particular?
And I don't in any way mean an argument and challenging Google, which I think is a fantastic thing and a fantastic company. But when I go in and do a search on a car, you do gather that information. So the next time I do a search, and I'm actually not bothered by that. I think it helps.
Yeah.
But there are ways that this could be used in a negative way, I would assume. And I'm really just trying to understand what can be done. How much, if someone wanted to use big data, they could aggregate into a personal profile. And I'm sorry for the follow-up.
Right. Yeah. So that's right. We certainly have a record of what you do, and I think a lot of it is an education issue of getting people to understand what is it that's being stored, what is it that's being kept, what's being deleted at what point, and all the companies have policies for that, but nobody likes to read through these long documentations, so you may not understand what your choices are. But for those who do care, you can go in and say, okay, I want this to be recorded, I don't want this to be recorded, so maybe I won't log in and reveal my identity when I'm performing these particular actions. And that's always the choice of the user, but I admit it's a really complicated choice, and it's hard for the users to understand what their options are.
Thank you very much. That was fascinating. I'm curious, as these algorithms become increasingly more powerful, how do you see the relationship between proprietary and open source software?
Yeah, so proprietary versus open source software. I guess part of it is that maybe the software is becoming less important and the data is becoming more important. There haven't been that many good examples of open source data. And I think in the scientific community, people are just starting to talk about that, saying how can we share our data. There have been some attempts, like in the search engine domain, to have open source data, and they just haven't gone that far. I guess maybe consumers just aren't that interested in having that, and maybe they'll emerge over time. I guess you could say something like Wikipedia is open source data, right? So everybody's contributing to that, and that's a high quality piece that everybody appreciates. And I think we can try to encourage that. Some of these have been self-supporting through the efforts of volunteers, through donations from their users, and from donations from corporations or philanthropists that support them. So I think we'll see more of that. I think we'll see people saying, well, maybe the proprietary software isn't what gives me the advantage. Maybe it's elsewhere, and so that's good for open source.
Please join me in thanking Peter for a just fascinating talk.